Hello and welcome back. Today we cover inverse trig functions. Day number 1. You can see there's actually 3 different days allotted to inverse trig functions. They're very important. So today will be our introduction. We'll cover these sections in the book. Project 6 is officially due at whatever date you see over there on your calendar. And then quiz 6 you should try to do on the next class. It's on the material 19, 20, and 21. Also note that the required form is coming up due, so look for a date right there next to that number, and know that 2 classes later you're expected to have some thoughtful response to one of your classmates' posts to this forum. So hopefully you're working on that soon too. After our 3 days on inverse trig functions, we have 1 review day, and then test number 2, which covers all the material since test number 1. So everything starting here and going down to there. And again, take a look at your particular calendar to know exactly when you're going to be taking test number 2. Okay, so let's go to the class notes. Number 1, in this lesson we introduced the all-important inverse trigonometric functions. These functions will allow us to solve equations where the unknown is an angle. We have not done that before. This topic is tricky for many students, so I've allotted 3 class periods to it. Let's take our time and make sure everyone is on board. Our ultimate goal for this topic is to be able to solve problems like this. The depth of water at a dock fluctuates according to the formula d equals 7 sine pi over 6t plus 32, where d is measured in feet and t is measured in hours since midnight. Find the first 3 times after midnight when the depth of the water will be 29 feet. So those are the kinds of problems that we're interested in solving. And in order to solve this particular problem, what we're really doing is changing the d into a 29 because we want to know when it's 29 feet. And so you can see that that has been written down here as this equation. And so the goal is to solve this equation down here for t. And the t is buried. And for the first time, we're trying to solve an equation where the t, the unknown, is inside of a trig function. That sign of something where the t is inside the sign. And so in order to solve that equation, we're going to need to use this idea of inverse trig functions. So number 2, we'll work up to solving the above equation. It's kind of complicated, but we start with much simpler ones. We'll use the unit circle on these. So part A, solve cosine theta equals a half for theta between 0 degrees and 360 degrees. So let's go back to the unit circle. Hopefully you've got it all filled in. And we're going to use that to solve cosine theta equals a half. So here's our unit circle. And we want cosine to equal a half. So we're going to write this up here temporarily. Cosine theta equals a half. Now we know, so we're looking for an angle so that the cosine of that angle is a half. And we know that cosine is at the x or the y coordinate. So we know that cosine is really the x coordinate. So this problem is really asking us to find all the points on the unit circle where the x coordinate is a half. Okay, so looking at some x coordinates here, not a half, not a half. Oh, that's a half. Super. So that third one right there is a winner. Just want the x to be a half, so we'll actually highlight that one for real. So that's good. Then we're looking at other places where we want the cosine to equal a half, which means the x is a half. That's not a half. That's negative a half there, which is not a half, so it doesn't work. Not a half, not a half. And you keep going around, but you might be able to get there faster than I am. Ultimately, you should see that there's actually a second point where the cosine is a half, where the x is a half, and that's down here at the bottom, right there. So we've got 2 answers to this equation. Cosine theta equals half. And again, the unknown is theta. So we're after not the points themselves, but the angles that created those points. So which angle was the one that led us to this x of a half? Well, it's this angle in here, which apparently is 60 degrees. So 60 degrees is one answer. And then the other answer that we want is the one that gave us this 1/2 here. And that angle right there, well, you could say negative 60. In fact, I'll write that on the other page. But negative 60 is not allowed. We need to say 300. So 300 is our answer right there. And that's the winner because the problem said find the answers between 0 and 360 degrees. So let's go back to where we were. And we're going to write down our 2 answers from the unit circle. We saw that one answer was theta equals 60 degrees. The other answer was maybe theta equals negative 60 degrees, but we're going to cross that off because it does not live between 0 and 360, and instead we'll put theta equals 300 degrees. So those are the two answers. Those are the only two answers between 0 and 360 degrees. Number two, or part B, solve cosine theta equals a half, same equation, but now theta is between 0 and 2 pi, which means we're thinking about radian angles. And you can go back to your unit circle. I'm not going to pull it up, but it's going to be exactly the same points because we still want the x-coordinate, cosine, to be a half. So it's going to be the same angles, but you're just going to grab the radian answers instead of the degree answers. So the radian answer here is pi over 3. And then I'm not going to put negative pi over 3, but we'll just put the one that works. So the one that works is 5 pi over 3. And those are our two radian answers. And then we come down here to part C. It says solve cosine theta equals a half. All right, well, that's kind of interesting because it doesn't give us a domain like we had here, 0 to 2 pi or 0 to 360. So I guess we're free to choose whether we want to think about this in radians or degrees. Maybe we'll do both. But what's weird is that you know, we've got our answers, 60 degrees and 300. Are there any more? And the answer is yeah. There's actually a lot more. If 60 degrees worked, that was the first one that we found. This point up here was a half, and then something that we don't care about. It was root 3 over 2. But it doesn't matter what that is. Then certainly going around a complete revolution and then 60 degrees more will also work. So 360 plus another 60 is 420. So 420 is a perfectly good answer. And so is going around 2 complete revolutions and then another 60 beyond that. And so there's actually infinitely many answers that land just on the 60-degree angle. And that doesn't say anything about the other infinite family of answers that land on the 300. So we got to come up with a way to write down 2 infinite lists of numbers, but we don't have a whole lot of time to do it. So we got to be clever about it. So here's our answer. Okay, so we're going to write theta equals 60 degrees, and we're going to write theta equals 300 degrees. Those are our 2 fundamental answers. And then I'm going to say, okay, you could have been at 60, or you could have gone around 360 degrees and then landed at 60. Or you could have gone around 360 degrees twice, or 360 degrees 7 times, and then another 60. So the way we're going to write this is 360 times k, where k is any old integer. And so that gives us, for example, if k is 1, 60 plus 360 times 1 is 420. That's the red angle that we've got over here. If k is equal to 2, then 360 times 2, that's 720, plus 60 is 780, which is this green angle in here. Or k could be 153, and you get many, many, many iterations, and then eventually landing back on the 60-degree line. The k could be negative, actually, so it means that you could go the other direction. Can't do that. So if k were -1, it would give you actually negative 300 degrees, which is a perfectly good answer. So, so we get all of them that way. And then we do the same thing with the 300 degrees plus 360k. K is an integer. Okay, so that's the double infinite family of solutions, and those are all in degrees, so we could just as well have given the answers in radians. So we could say theta is either pi over 3, that was one fundamental solution, or theta is 5 pi over 3, that was the other fundamental solution. And each of them, we're going to have to add not 360 times an integer, but rather 2 pi times an integer. 2 pi times k. For both of them, again, k is an integer. So it is very typical for trig equations to have infinitely many answers. In fact, to have 2 sets of infinitely many answers. That is the most common answer to a trig equation. Moving on to 3, let's solve sine theta equals negative root 2 over 2 for theta between 0 and 360, and then for theta between 0 and 2 pi, and then in general. Okay, so we want sine theta to be negative root 2 over 2, so we'll go back to our unit circle to help us. Okay, so we'll get rid of what we had before, which was this, and then we'll write the new equation. So sine theta is negative root 2 over 2. Now, it happens that that guy's already been rationalized. The denominator has already been rationalized. I can see some root 2's in this problem, but it's not in the right spot. It's just because the root 2 over 2 has been written in a slightly different form. But if we were to take this guy and multiply by root 2 over 2, or root 2 over root 2, I should say, then get rid of this. Then we see that we get negative, and then on the top is just a 2, and on the bottom is 2 times root 2, and the whole thing turns into negative 1 over root 2 when you cancel the 2's. So this is really saying when is sine theta equal to negative 1 over root 2? And negative 1 over root 2 is a number that you'll find on this page many times. So that one will translate just because we've written things on this page in a certain way. So is the sine the x or the y? So we know that's the y. So this problem is really asking for all the places on the unit circle where the y coordinate is negative 1 over root 2. So pause the video here, see if you can find 2 places where the y coordinate is negative 1 over root 2. Okay, so hopefully we found them. We want the y coordinate to be negative 1 over root 2, and I see that happening twice. So the y coordinate is negative 1 over root 2 right there, and also right here. And so we've got our 2 answers, but again, we were looking for an angle as the final answer. So we want to know which angle lands on the 2 points we just highlighted. So here's the angle right there. So it looks like that angle is 225 degrees, or 5 pi over 4 radians. And then the other angle that worked was this one right here, which looks like it's 315 degrees, or 7 pi over 4 radians. So those are our 2 answers. Okay, so from the unit circle, we got theta is, on the one hand, 225 degrees, or, and the other answer was 315. And we'll pick a different color here in radian mode. Theta was 5 pi over 4, or 7 pi over 4. And then we want to solve the equations in general. So let's write this in yet another color. So in general, theta is 225, and you got to write a separate equation. Theta is 315, and then we're just going to stick on the plus 360k. 360k. So again, 2 infinite families of solutions over here. Whether you're in degrees or radians, doesn't matter. You got to write these equations separately. And to each of the fundamental solutions that I've just written, we're going to add not 360 times k, but rather 2 pi times k. It's always 360 or always 2 pi. That's our way of just saying go around as many complete revolutions as you want, but once you're done wasting time, then just add the fundamental solution and you will land on the right spot. Number 4, let's solve cosine theta equals negative 1 for theta between 0 and 360, and then for theta between 0 and 2 pi, and then in general. So here we want cosine to equal negative 1, so we'll go back to our friend, the unit circle. Okay, so we're looking for places where cosine is negative 1. We'll write that up here. Cosine theta is negative 1. Is the cosine the x or the y? Cosine is the x, so here we want places where the x is negative 1. In fact, there aren't 2 points on the circle where the x is negative 1. There's only 1. So we'll highlight it here in green. That point right over there is the only place where the cosine is equal to negative 1. It's the only point on the circle where the x coordinate is negative 1. So then the answer to this problem is the angle. It's 180 degrees, or pi radians. Okay, so we'll write that here. So our answer is theta equals 180 degrees, or separately, theta equals pi radians. Those are the only answers if we're looking between 0 and 360 or between 0 and 2 pi. But if we want to write our solution in general, we say, okay, you could go 180 and then another 360 times any integer you want, or you could go pi and then another 2 pi times any integer you want, and that's it. But I want to be really clear, this is a special case. Normally, you have, for a trig equation, 2 fundamental solutions which lead to 2 infinite families of solutions. Whether you're in degrees or radians, doesn't matter. You're almost all the time going to have 2 fundamental solutions and then a double infinite family of solutions. We saw the same thing up here. 2 fundamental solutions, double infinite family of solutions. But the special case happened because we were exactly at the extreme point of the circle. We were at the far left-hand point of the circle. There was only 1 point out there instead of having 2. Next page. Let's estimate the solutions of cosine theta equals 0.45 between 0 and 360 and between 0 and 2 pi. So we're looking for cosine to equal 0.45. We'll go back to the unit circle. And we'll write the equation here. Cosine theta is 0.45. And again, we'll translate. Cosine we know is it the x or the y? It's the x. So here we want points on the circle where the x is 0.45. Okay, let's see if we can figure this out. So I'm just going to look for a place on the x-axis where the x is 0.45. So I know that, that if I go halfway, then we get 0.5. And 0.45 is slightly to the left of that. So actually I can do a little better with estimating the halfway point because the halfway point is this yellow highlighted one, right? That's the place where x is exactly 0.5. So I'm just going to do my best to drop that straight down and then we'll erase this in a little bit. So that right there is at 0.5. And so that means that 0.45 is slightly to the left of that. So maybe we can estimate right here, 0.45-ish. And so all we do is go up from there and we hit a point on the circle that's just a little bit higher than the one that we had before. But there's another point on the circle where the x is 0.45, and that's down here. And this one's a little lower than the other yellow highlighted one right there. And again, the answer to these problems is supposed to be an angle. So we're going to be looking for the angles that land on these 2 red points. So the angle is going to be this one here. Okay, now that angle is very close to the 60-degree angle that's still the highlighted in yellow one. Is this angle a little more or a little less? It's a little bit more. So if you wanted to say like 62 degrees or something like that, that would be okay. And then down here, the answer that we had before was 300 degrees. We're looking for something quite close to that. We want the one that goes out to this red point. I can do better. So is that angle right there? I can still do better. Is that? No. Leave it to me to record and then not have any idea how to draw a straight line. So is that angle right there a little bigger or a little smaller than the 300 degrees? Hopefully we see it's a little smaller, although if you can't based on my diagram, I wouldn't blame you. But this angle is a little bit less than the 300, so if we said like 298, that would be okay. And in terms of the radian answers, they're going to be messy numbers. Let's go up to the one on the top and say that the close answer, this one here, the 60-degree answer was pi over 3. So we can just type pi over 3 on the calculator and get an approximation there, and then we can tweak that number just a little bit. Okay, so let's try pi over 3 here. So about 1.047. So the angle that I want with that red dot, is that a little more or a little less than the pi over 3? It's a little bit more. So if you said 1.06 or 1.08, something like that, then that would be fine. And we can do the one on the bottom too, which was 5 pi over 3. 5.236-ish. The angle that we really want though with this red dotted stuff is a little bit smaller. So if you said 5.22 or 5.21, anything like that. Again, we're just estimating here. Okay, so let's get our estimates onto the page that we were on before. Okay, so the degree answer that we estimated, first one was a little bit more than 61 degrees. So we'll say something like theta is roughly maybe 61 degrees, or roughly we wanted something a little smaller than the 300, so maybe 298. Or in radians, we have our 2 answers that we had before. So again, looking at the calculator, we had 1.047 The true angle we wanted was a little bit bigger than that, so maybe 1.05, just estimating. Or theta is approximately, and then we got this 5.236, and we wanted something a little smaller than that, so maybe something like 5.22. And it might not feel all that great to just be guessing at these numbers, but there's a way that we can use the calculator to help us not have to just guess so blindly, and that's listed here in number 6. In the equation cosine theta equals 0.45, we need to undo cosine. Inverse cosine to the rescue. Let's take the inverse cosine, denoted cos to the -1, or arc-cos, that's pronounced arc cosine. We'll take that of both sides and then use the calculator in 2 different modes. So I'll just say that if you see arc-cos, you can read that arc cosine. Okay, so let's write our equation again. Cosine theta is 0.45. And actually, I'm going to leave a little space in here. And what we're going to do is the same thing to both sides. And the thing that we're trying to do is solve for theta. And the way we solve for theta is to get this cosine out of here. So we need something that undoes cosine, and apparently mathematicians call that thing inverse cosine. So in the same way that, for example, if you had to solve this equation, you would subtract 7 from both sides because that's undoing this plus 7. Or in this equation, you would divide both sides by 3 because that's undoing multiplying by 3. We're going to do the same thing to both sides here, and that same thing is going to be to undo cosine, but it is wrong to divide both sides by cosine and think that we're going to be able to cancel the cosine here with the cosine here and just get theta. Dividing by cosine doesn't make sense. Just saying cosine without immediately following it with an angle also doesn't make sense. So this isn't cosine times theta, so division is not the right operation. The right operation is inverse cosine. So we're going to take the inverse cosine of both sides. And the idea is if you do the same thing to both sides of a true equation, you'll still have a true equation. And the point is that on the left-hand side, we have inverse cosine, whatever that is, of cosine of theta, and that's simply theta. And that is a definition. Inverse cosine is exactly the thing that we invented to cancel with cosine. So without even having a firm grasp of what inverse cosine is, or what it looks like, or what it, or how it behaves, just know that it is the thing that we have invented to cancel the cosine function. So inverse cosine of 0.45, whatever that means, that's the answer to this problem, and that's a definition. So how do we get the answer as something that we prefer? Well, we have an inverse cosine button. It's right here, right above the cosine. You can see in yellow, it says cosine to the -1. And so we'll clear this here, and we're going to type in second cosine. Okay, there it is right there, cosine to the -1 of 0.45. Remember how I've been saying all semester that anytime I hit one of these 3 buttons, sine, cosine, tangent, I check my mode? Well, I just hit one of them, even though I hit the yellow button first. I still hit the cosine button. So I'm going to check my mode. I'm going to go into degree mode first, just because that's how we answered the problem first, and then we'll switch. And then we're going to delete this. Okay, and we are expecting some number that is roughly whatever we got before. So what we got before was 61 degrees and 298 degrees. So let's come back and come back. So something around 61 and or 298. Let's see how well we did. 63, we did okay. I underestimated at 61 degrees, but 63.2563 is a very good approximation for the right answer. And to double check, remember we were looking for an angle, so the cosine of that angle was 0.45. So if I type in as many digits as I have patience to type in, you should see that you should have some expectation as to what the calculator is going to say when I hit enter. Something very close to 0.45. It's not exact because this isn't exact, and I also rounded it here at the end. So if I had typed in a few more, we had gotten some more zeros, but that's the magical angle whose cosine is 0.45. So about 63.256 degrees. Okay, now we could just as well do this in radian mode. So let's do it in radian mode. Let me clear that. I'm going to type it again, just like we had it. Inverse cosine of 0.45. So we've got that same number we just saw. Now I'm going to go in here and change my mode to radian mode. And then we're going to see something quite disturbing to some of you. I'm going to type exactly the same thing that I type above, and I'm going to get something completely different from what I got above. And for somebody that doesn't know that we changed modes between typing in those two things, that's going to look very confusing. Like the calculator doesn't know what the answer is, and it's just going crazy spitting out random numbers. So 1.10, what is it? That's the radian version of the 63 degrees that we got up above. Okay, 1.104, what did we guess? In radians, we guessed 1.05, close enough. So our estimate here, 1.10403. Okay, moving on to number 7. Inverse cosine is defined to be a function, so we will only get one output for cosine inverse of 0.45. We knew that we had two answers up here in black. We were expecting about 61 degrees and about 298, although looking at those, they're not symmetric with each other, but whatever. But we expected two answers, and the calculator is only going to give us one, ever. Calculator is programmed so that when you type in inverse cosine of 0.45, it is always going to give you this 63. It will never give you the 298 answer up above. It's only going to give you the 63. And we got to do a little bit of analysis to get the calculator to give us the other one. So thinking about symmetry, let's draw a picture here. So we'll draw our unit circle. And we knew that one answer was this 63 degrees and change. And that was a place where the x coordinate was some magic number. It was 0.45. So we can come down here and say that right there is 0.45, almost 0. And we were looking for the other point with exactly the same x coordinate. And so we can just keep going down here. We know it's this point down here. And so the angle that I really want is going to be this one going around to there. And we can use symmetry. And we can know definitively that this little tiny angle in here has got to be the same 63 degrees and change that the other one is. Negative 63 if you want to call it that. And then we'll just use symmetry and say, okay, then the other angle that I wanted was really 360 minus the 63.256. And so what do we get here? 296 point, what is that, 744? Maybe that's okay. So that's it. So that's the other angle. I don't trust my arithmetic, so we're just going to do this before we go too far. 360. Actually, let's go back up and get this other answer. Okay, and then we can do 360 minus that answer. I always like to use as many digits as the calculator will show me and then some. Okay, so I think we did okay here, 296.744 degrees. And if we wanted the radian version, we had the 1.1043, that was up here. But we want the radian version, so 1.1043 apparently is this angle here in radian version. So we're going to do not 360 minus, but 2 pi minus. So that's how we'll get the other answer. 2 pi minus this 1.10403. Okay, here I'm definitely going to use the calculator, so let's try this one. And just like before, I'll get as much accuracy as I can by asking the calculator for inverse cosine of 0.45, and then doing 2 pi minus this answer. 5.179, so that's our second number. Okay, so we use the symmetry on the unit circle. You're also welcome to use symmetry on the graph of the cosine function. So you're just going to pick whichever way seems more natural to you. But for example, we know that the cosine function starts at the top and it's on its way down. So that's f of theta is cosine theta. And we were looking for places where the function, the cosine, was equal to 0.45. So we can go to 0.45, which is right around the middle here. And we can just shoot straight across from there. And we're going to see that we have two solutions. And so the first solution was this one right here, and it turned out that that was around 63 degrees. My diagram is not really to scale, but that's okay. So if it's 63 degrees in here, then it sure feels like it's going to be 63 degrees here, where the end of the game is at 360. And so just like before, we're going to do, to find this number right here, we'll do 360 minus the 63. And that's exactly the calculation that we did here. So whether you're a unit circle person or a graph of sine and cosine person, makes no difference. You're going to pick one that feels good to you, and then think about the symmetry. Number 8, in the previous problem, theta equals about 63 degrees and theta equals about 1.1 radians are called reference angles. You'll read about them tonight, and we'll use them a bunch today and in the coming classes. Number 9, let's estimate the solutions of cosine theta is 0.45 for theta between negative pi and 3 pi. Okay, so we've already got our fundamental answer. The calculator told me that theta was around 1.104. Am I missing a zero there? 10403. Okay, so we'll say around 1.04. And that's fine. And then the next answer that we got, we just we took 2 pi and then subtracted this guy, and then we got the 5.179 that we saw before. That's fine. But we're trying to get an answer that goes all the way up to 3 pi, which is kind of far. So how do we get one that's up to 3 pi? Well, we actually know how to get them all. We know that we can add 2 pi times any integer to the 1.04 or to the 5.179. And that's all the answers, the double infinite family of answers. So what if we just use our calculator here, and we'll get this 1.104 business up here. So inverse cosine 0.45, it's there. Let's try that again to clear screen, so it's there. And then I can just add 2 pi times this thing. And that right there is another answer that's smaller than 3 pi. Right, so 7.387 is another winner for us. So theta equals 1.04 plus 2 pi is around 7.387. And that's another angle that works. What if we get greedy and we add 2 pi again? So let's go back to inverse cosine of 0.45. Nope. Inverse cosine of 0.45. And what if we decided we wanted to add not just 2 pi, but actually 4 pi? So we could do 2 pi times 2. In this case, it's 13.67, which is too big because there's 3 pi sitting at the top. So 13.67 is too big. What if we tried taking the other answer, the 5.179, and adding some 2 pi's to that? So let's try that one. I probably should just store this inverse cosine of 0.45. So why don't we store that as x? Okay, so we did 2 pi minus that answer. And that gave us the 5.179. And we could add 2 pi to this. We can add any number of 2 pi's to this and get perfectly good answers. So 11.46, is that okay? No, that's also too big. Because remember, 3 pi was around 9 and change. So that's no good. But what if instead of adding 2 pi, we subtracted 2 pi? Because you don't have to just add positive integer multiples, you can subtract. And we get negative 0.5179. Well, let's see, is that okay? Well, we know, what did we do? Oh, that's not what I meant to do, but that's okay. What I just did was took the x, which is the 1.04, and subtracted 2 pi. And I get negative 5.179, which is a perfectly good answer. And in this case, it's too small because according to the problem, we're only looking for answers that get down to negative pi. So that's around negative 3 and change. So negative 5 and change is too small. But what if we took our other answer? So I'm going to do my 2 pi minus x business just to get my other fundamental answer. And then I'm going to subtract 2 pi from this. We tried adding 2 pi to it, and it was too big. But if we subtract 2 pi, well, it's okay. Negative 1.10403 is within the acceptable range. or domain, I guess I should say, it's inside of negative pi to 3 pi. So we're going to write that answer here. So we did our 5.179, and then we subtracted 2 pi, and we got negative 1.104, which is another valid answer to this problem. I realize here I have a 1.04. It should have been 1.104. Okay, so I think we can highlight and get all of the acceptable answers here. So we have 1.104, we had 5.179, 7.387, and then finally negative 1.104. So 4 different answers to this problem based on the domain that was given, this negative pi to 3 pi. Okay, number 10, let's again solve sine theta equals negative root 2 over 2 for theta between 0 and 360, but this time we'll use the calculator. Okay, we can do that. So I'm going to copy my equation again, leaving a telltale space here on the right-hand side of the equal sign. And that space is where we're going to insert the thing that we need that's going to undo the sine function. So just like inverse cosine undoes cosine, inverse sine undoes sine. And so we're going to take the inverse sine of both sides. We're not multiplying by inverse sine. That doesn't make sense. We are taking the inverse sine as a function of both sides. And again, the whole point of this is that on the left-hand side, inverse sine and sine cancel, and we're left simply with theta. And so we just get inverse sine of negative root 2 over 2, which we can type into the calculator. Now, it turns out it's a nice number, but we can type this into the calculator. So let's do that. So we do inverse sine of, what do we have here? Negative root 2 divided by 2. Now before I hit enter, again, I got to be aware, I hit sine, cosine, or tangent. I need to think about my mode. This problem says be in degree mode, so we got to hit that in degree mode, and we get negative 45 degrees. Now is negative 45 degrees one of the answers we got to this problem before? I actually don't think it is. So let's go back to down here. So we solved this problem already. It was this one. And we got 225 and we got 315. Negative 45 degrees, well guess what? That's the same as 315. I don't know why the calculator chose to tell me negative 45 instead of 315. And I don't know why it's giving me no sense that 225 is also an answer. We have work to do there. But negative 45 is perfectly good, and it's our job to make that land in the right domain. Okay, so according to the calculator, this is negative 45 degrees. That is not an acceptable answer for us for this problem, because this problem says make sure that you are between 0 and 360. So negative 45 degrees. We can draw a real quick picture. And negative 45 degrees is in here, which means that the true angle had better be everything else, or the true angle, the positive version of this angle, must be 315, right? So we can take 360 and add it to negative 45, and we get 315. But remember, there's always 2 fundamental answers, and we saw on the other page that the other answer was 225, but the calculator will never give you 225. So we got to use the symmetry of this picture. Okay, so think again about the fact that we are solving this sine equation. Is sine the x or the y? It's the y. So we were looking at this special point right here the calculator gave us, and it turned out that the y coordinate there was something special. It was negative root 2 over 2. And you got to find the other point on the circle with the same y coordinate. Hopefully you can see there's only 4 choices. You either go straight up, straight left, or straight through the origin. You get kind of this square shape here. So only one of them has exactly the same y coordinate as the one that we just wrote down. And it's, hopefully you can see it's this one right over here. At that point, y is also exactly negative root 2 over 2. So then we can, let's see, we can draw in here purple. So the angle that I want must be this. But looking at the symmetry, I guess I got to believe that's also a 45 degree angle in there. So then the purple angle must be 180 plus that 45. And that 180 came just because we took our time and drew a really good picture. And so you got to make sure you're drawing a really good picture, because otherwise the 180 will just kind of seem like it's out of the blue. Okay, so we got our 315 and we got our 225, which agrees with what we said before on the previous page. Okay, next page. Now solve sine theta is negative root 2 over 2 between 0 and 2 pi by using the calculator. So same as before, I'll copy the equation, I'll leave the telltale space, I'll fill that space with the inverse sine. Doing that to both sides, canceling on the left-hand side, and just getting theta is the inverse sine of negative root 2 over 2. It's exactly the same thing that we wrote before. It's good practice. And then coming down here, we're going to type in exactly that same thing that we got up above. The only difference, though, is that we need to be in radian mode for this problem. So we hit enter, and we get this maybe strange-looking decimal that we haven't seen before. If you go back a couple of pages, what did we get for the exact answer to this problem when we used radians and the unit circle? So hopefully you see that we got two answers, 5 pi over 4 and 7 pi over 4. Just for kicks, I'm going to type in 7, you know what, I'm going to type in just pi over 4. And lo and behold, exactly the same decimal, but a positive instead of a negative. That kind of makes sense. If you think about the point that we picked on the unit circle, it was at negative pi over 4. We just chose to write that as 7 pi over 4. So that's just a coincidence. We have a nice number up here. I guess I shouldn't say it's coincidence, but the fact is it's not normally a nice number. So we need to be able to handle when it's not normally a nice number. So we'll say about 0.785 radians. And you got to use symmetry. You got to draw yourself a really nice picture. And negative 0.785, even if you don't know it's this negative pi over 4, you should know that up here at the top, pi over 2 is about 1.5, and pi is about 3, and 3 pi is about 4.5, and then 2 pi is about 6. Those numbers aren't perfect, but they give me a sense that negative 0.785, well, if this is only 1.5 up here, then negative, or then 0.785 would only be like halfway, except it's not up there, it's actually negative. So the thing that we're looking for is in the fourth quadrant. And so we'll say this number right here is roughly negative 0.785. And then we got to use the symmetry to find the other fundamental answer. Let's first take this guy and add 2 pi to it. And so we'll get a number on the calculator. So we'll do 2 pi. Let's actually clear this and retype that thing so we have as much accuracy as possible. Okay, so we had that one, and then we're adding 2 pi to it to give us the positive version. So about 5.498. Okay, so that's one answer. And then we need the other answer, and we play the same little game that we played before. We knew that we were looking for a special sine value, that is a special y value. The other point that has the same y value is here. So then by symmetry, this has got to be a 0.785 in here. And then the true angle that we want must be this one, which is pi plus 0.785. Okay, so I'm just going to be lazy. Pi plus 0.785. So about 3.927. So those are our two fundamental answers. Those are the only two answers between 0 and 2 pi. We'll highlight them, this guy and this guy. And just to make sure that that agrees with what we got before, again, you can go back a couple of pages, but the two answers we got to this before using the unit circle were 5 pi over 4, that was the first one, and then 7 pi over 4. And those better agree with the two answers that we got highlighted there on the right. 12. Mathematicians have made the following choices so that the inverse trig functions are functions. That is to say, we'll never get two different answers when we type in inverse sine of negative root 2 over 2. These are the choices that are programmed into every calculator and computer, and they are the choices that we are all bound to follow. We'll use the graphs that follow to motivate the choices, and we'll write our answers in interval notation. Okay, inverse sine of t. All right, let's take a look at the sine function. It's this first one. The reason the sine function has no inverse is that it fails the horizontal line test pretty badly, actually. You can draw a horizontal line that hits the sine graph more than once, in fact, infinitely many times. That's very bad. So what we're going to do is restrict the domain of the sine function so that the restricted sine function passes the horizontal line test. So I'm going to start here at the origin. That seems like a natural place to start. We're going to go up to the top, and I'm going to stop there, because as soon as I start coming down, I have a problem with the horizontal line. So we're going to stop at the top, but then we're going to continue on to the left from the origin, and we're going to go all the way down to the bottom. And then we're going to stop at the bottom, because as soon as you go up, then you've got problems with horizontal lines down there. So I feel like from the very bottom to the very top, we've got the entire vertical covered, right, -1 to 1. But we've gone as far as we can before we lose the fact that this guy is invertible. At least the purple part of it is invertible. So looking at the numbers that are here, let's see, that's a pi over 2 at the top, and that's a negative pi over 2 at the bottom. So in terms of the domain and range of inverse sine, well, all we have to do is reverse the numbers that we've got here. The domain of this purple thing that I've just written is negative pi over 2 to pi over 2, so that becomes the range. Negative pi over 2 to pi over 2. Brackets on both, including both. Looking at the range of the purple thing that's drawn here, so we can see that the range, this curve starts down here at the bottom at -1 and makes it all the way to the top at +1. That's the range of the sine function, which becomes the domain of the inverse sine function, -1 to 1. Okay, and so what that means is that you can plug into the inverse sine function any number between -1 and 1, any number at all, and the answer that you get out will always be between minus pi over 2 and pi over 2. No matter what you type in, inverse sine will always give you an answer between minus pi over 2 and pi over 2. Okay, and then in terms of quadrants, I think we've drawn this before, but we can superimpose the quadrants here. We know that the first quadrant goes 0 to pi over 2. So this right here is quadrant 1, and then the second quadrant goes out here to pi, and then third quadrant goes to 3 pi over 2, and then the fourth quadrant goes up to 2 pi, and then they just continue over here. So there's the fourth quadrant. So I guess what we're saying is that the purple only corresponds to quadrants 1 and 4. So whenever you use the calculator, you're going to get an answer that is in the first or fourth quadrants. That's the minus pi over 2 up to pi over 2. Okay, looking at cosine, it's the same idea. I'll start here at the top of cosine. I will work my way to the bottom of cosine, and then I will stop, because as soon as I continue, we've got horizontal line problems there. If I continue this way, horizontal line problems there. Okay, so looks like 0 to pi is the natural choice for cosine. So let's write that up here. And then it's the same -1 to 1 for the domain of inverse cosine. And then in terms of the quadrants, so just thinking about the angles that are between 0 and pi, that's the first and second quadrants. And anytime you hit the inverse cosine button on your calculator, you will automatically get some answer that is between quadrants 1 and 2. Okay, and the last one here is inverse tangent. That picture is on the next page. So what we're going to do is draw in purple one branch of the tangent function. That's that one. And that branch is fine. As soon as I start drawing on another branch, I have horizontal line problems, so we won't do that. And we'll just remind ourselves that we had vertical asymptotes here at pi over 2 and negative pi over 2. So those are going to be the important numbers for inverse tangent. The only difference here is that pi over 2 is never part of the graph. It never hits up there. It's an asymptote. So instead of including pi over 2, it's actually going to be parentheses because pi over 2 is not an allowable answer. So let's go back and fill in. So we just decided that negative pi over 2 to pi over 2 goes here, but it's not including either one. And then the domain here is actually quite different. Where does the tangent function start at the bottom? It starts at minus infinity. It goes all the way forever. So the domain here is all real numbers, minus infinity to infinity. And the quadrants that we get, it's the same answer as up here, right? Minus pi over 2 to pi over 2. So it's going to be the same quadrants here, 1 and 4. Okay, so those are choices that mathematicians have made and that programmers have plugged into your calculator and in your computer. And you just need to be aware of those choices so that you know what to expect and know how to handle the answers that your calculator gives. So let's look at 13. And we're going to see how to use the facts that we just established in that previous diagram. Find the following with your unit circle. No calculators allowed. Write your answers in radian mode. Okay, inverse cosine of root 2 over 2. So we want to go back to our unit circle. Okay, so inverse cosine of root 2 over 2. We'll go to our unit circle, and we can write this one over here. Inverse cosine of root 2 over 2. Remember this little calculation we did before. That's exactly the same number in there as 1 over root 2. So we were looking for the cosine to be 1 over root 2, and remember that the cosine is the x, so we want a point on this circle where the x is 1 over root 2. Okay, well I see 1 in front of me, it's right here, but there's another one. And the other one is down here where the x is 1 over root 2. So it seems like I have two answers to kind of contend with, 315 or in radian 7 pi over 4, or up above the 45 and pi over 4. So how do we know which one is right? Well, actually, it could be neither one is right, but what we need to do is use some of these facts we've established here. We are looking for the inverse cosine of root 2 over 2. We want the answer to that problem, which means we're thinking about the range of inverse cosine. So coming back to our previous page, we saw that the range of inverse cosine is always 0 to pi. So anything that we answer to this problem has to be between 0 and pi. Okay, well that narrows it down for us. Remember we had two choices here. It was either the 45 degrees pi over 4 or down here 315 and then 7 pi over 4. We need the thing that's between 0 and pi. It's this one. 7 pi over 4 is too big. So the answer to this problem is pi over 4. Nothing more, nothing less. The other way to think about where you're going to find your answer is to use that quadrants business. We said that inverse cosine will always land in quadrants 1 or 2, so you just got to pick the angle that's up here. There's no point looking down there for inverse cosine. So pi over 4 is the answer to this problem. Okay, moving on to B, inverse cosine of negative root 2 over 2. So let's come back here. We'll just change this to negative root 2 over 2, which is negative 1 over root 2. It's still the x that we're looking for, but now we want it to be negative 1 over root 2. So I'll highlight here in green. Negative 1 over root 2 for the x, it's there. And it's also down here. But again, inverse cosine will always land in quadrants 1 or 2, so there's no point looking down below. The answer to this problem is the one that's up above, which is this angle going up to here, 3 pi over 4. Okay, so far so good. Let's take a look at this next one. Inverse sine of negative root 3 over 2. Okay, inverse sine, negative root 3 over 2. Okay, again, we are looking for inverse sine, so that's going to be a y value. So we want the y to be negative root 3 over 2. So the negative y's happen down below, so we'll focus down there. Negative root 3 over 2 for the y. It happens here, and it also happens here. But now we got to think about this is an inverse sign, so we'll go back a couple of pages. Inverse sign always lands in quadrants 1 or 4. It's different from inverse cosine. And it's always between minus pi over 2 and pi over 2. That's the only choice that we have. So it's quadrants 1 or 4, so I guess that means we can eliminate this one, which we highlighted. That's in quadrant 3. So it's got to be this one over here. And this one over here, the answer is either 300, but we're doing radians, so 5 pi over 3. So it feels like the answer is 5 pi over 3, but it's not. And I can convince you it's not by just asking the calculator what the answer is. And I can assure you it's not going to tell me 5 pi over 3. So I'm typing in this thing right here, inverse sine of negative root 3 over 2. And again, anytime I hit those buttons, I got to go to the mode. Okay, radian is the right place to be. We had suggested that the answer to this one was 5 pi over 3. All right, so 5 pi over 3 is something around, 5, 5.5. But it is definitely not that. Okay, what's going on here? Well, we had said more than just quadrants 1 and 4. We actually said the answer was always between minus pi over 2 and pi over 2. So you can't just pick something between quadrants 1 and 4. You got to pick something in this range. So apparently, instead of going around 5 pi over 3, which would be from here all the way around, apparently we were supposed to go the short way, which is the negative way. So instead of going around, we want to go this way. And hopefully we can see that this is pi over 3, but going backwards. So the answer to this problem is negative pi over 3. And just to get a little bit of confirmation, if I type in negative pi over 3, hopefully we'll get something that looks familiar. So that's what the calculator was telling us. Okay, part D, inverse tan of 1, and then E is inverse tan of negative 1. Okay, let's take a look. So we'll start with inverse tan of 1. Okay, now you don't see any 1s on this unit circle except for the extreme points. There's a 1 up there at the top, and there's a negative 1 over there on the left. So, but tangent we know. Let's see, so if this is some angle, then we know that tangent of the angle is supposed to be 1. Those are two different ways to say exactly the same thing. But we also know that the tangent of some angle is the y divided by the x. And the only way a fraction is going to be 1 is if the top and bottom are exactly the same. So what we're looking for are x's and y's, which are exactly the same as each other. And so, for example, if you look here, the x's and y's are different. But if you look here, the x's and y's are the same. So this is a winner right here, 45 degrees or pi over 4. But there is another point. Remember, almost always there are two different answers on the unit circle. So find the other point where the x and y are exactly the same. And hopefully we see it's here. But the range of inverse tan, you can go back a couple of pages, is minus pi over 2 to pi over 2, which is quadrants 1 and 4. So this angle in quadrant 3 is excluded. It's just a choice that mathematicians have made. So it must be this one right here, which is 45 degrees, which is pi over 4, which is the answer. Okay, next one is inverse tan of negative 1. So we'll just make some slight additions here. So that's a negative, negative there, negative there. So in this case, we want the x and the y to be exactly the same, but opposite sign. That's the only way a fraction can be negative 1. Top and bottom are the same number, but opposite sign. So you want x and y to be the same, but opposite sign. For example, right here, x and y are exactly the same, but one is positive and one is negative. And there's one other place where that happens, and it's down here. Same number, but opposite sign. And we know that that inverse tangent has a range that's between minus pi over 2 and pi over 2, or quadrants 1 and 4. So that means that this angle up here in quadrant 2, even though it seems like it's okay, it's excluded. It must be this angle down here, which means we're looking at 315 degrees or 7 pi over 4. But again, we got to be really careful. It's not enough to just pick the quadrant 4 angle. We got to pick something that's in the range. And the range for inverse tan is something that is always between negative pi over 2 and pi over 2. So you can't pick 7 pi over 4. That's not in the range. So we have to say, oh, I guess they didn't want us to go all the way around and land on 7 pi over 4 that way. They really wanted us to go backwards and say, oh, that's just pi over 4, but it's backwards, so it's negative pi over 4. So it's kind of a tricky game I'm asking you to play here. This whole domain and range business for the inverse trig functions, it's not easy. So give yourself some time as you work through the ideas in tonight's homework. The activity is here on the next page. Again, give it a good shot before you check out the video of me going through it.